Alright, so welcome back to the OneClass channel. Again, my name is Joey. I'm going to be your chemistry teacher for this session. So here at OneClass, what we're doing is that we're verifying and providing solutions to questions in both chemistry as well as mathematics in both secondary level as well as the college and university level as well. And what we're doing here is we're basically teaching you the concepts through through verifying solutions so that you have kind of the best resources going forward into your upcoming tests or any other future course that you might wish to take. So my name is Joey. I'm currently a secondary school educator in Ontario, and my teachable subjects are chemistry and soon to be mathematics as well. So I have 10 questions for us today. It's going to span in the high school curriculum, so in grade 11, grade 12, kind of chemistry questions, and then we will go through that and I'll teach you the concepts through those questions as well. So let's get started on today's problems. So our first question is asking us, what is the molarity of a solution that contains 17 grams of NH3 in a 0.50 liter solution? Let me just bring up the periodic table as well, because we're going to need to know. We're going to need to use this to figure out our solutions. So let me write this down. Wait a second. Okay, so let's see. So we have, I want the molarity of a solution that contains 17 grams of NH3 in 0.5 liters of solution. So what are we given first? Well, we're given our mass of our NH3, right? So mass of NH3 is 17 grams. And we're given our volume, right? Our volume of our solution is 0.50 liters. So in order for us to solve the molarity, what we have to do is we want to solve the molarity. Right? What we're given that we're asking the molarity, so you can say the concentration of our NH3 solution here is our unknown here. So what can we do to figure out the concentration? Well, I know that my concentration of NH3 is going to equal the moles of NH3 divided by our volume of our solution, right? So moles of NH3 divided by our volume of solution. So we are given our volume of solution. We know it's 0.50, but how do we figure out our moles of NH3? Well, we can figure out moles from our mass, right? And we know that our mass, or our moles of NH3, is going to equal the mass of NH3 divided by our big M, our molar mass of NH3 here. And we know that our mass here is 17 grams, so we can put that at the top. 17 grams NH3. Or you can just say 17 grams divided by, how do we calculate our molar mass of NH3? Well, I would have to go through my periodic table to figure out what is the molar mass of NH3, right? So I have how many? I have 1 nitrogens here. So I can say 1 times, I can look at my periodic table here. Nitrogen has a molar mass or atomic mass of 14.007. So in 1 mole, I'm going to have 14.007 grams per mole. So we can say 14.007 plus, and then I have how many hydrogens here? NH3, right? I have 3 hydrogens here. So I have 3 multiplied by, I look at hydrogens here, it's 1.008 grams per mole. grams per mole. So I have 17 grams divided by, so I'm going to use my calculator. So I have 1 times 14.007 plus 3 times 1.008 will get me a value of 17.031. This is in grams per mole. And then I can simply just divide 17 divided by that answer will give me the number of moles, which is going to be 0.998 moles. And that's actually the solution that they got here, which is great. And now if we're given our moles of NH3, the problem becomes very, very easy. I can just substitute the moles of NH3 into our equation here to figure out our concentration. So C of NH3, the molarity of ammonia is going to be 0.998 moles of NH3 divided by our 0.5 liters of solution here, which is going to equal 0.998 divided by 0.50 will give me a value of 1.996. And this is the big M for molarity, which is approximately equal to basically 2.00 molarity here. And this is our correct solution. And as you can see, this solution is correct because they got 2.00 as well. The solution is correct. So basically you find the moles and then you find the concentration after that. Very, very easy stoichiometric problem here. Okay, number 2, which salt is a strong acid, strong base salt? So I want strong acid, or let me write this, strong acid, strong base salt. I'm given 4 guys here, so let me write this down here. So I have NH4CN, I have LiNO3, Li3PO4, Na2CO3, and I have NH4Br. So what I would do is I would actually break this down into its kind of components here. And I would kind of dissociate these ions first, or dissociate the salt here into its ions to see what it could have been, give me an idea of what the acid and base could be. So this guy would be NH4 plus CN minus. This guy here is simply just Li plus NO3 minus. This guy here is Li plus PO4 minus. Guys, Na plus CO3 2 minus, and I'm going to balance these guys as well. Let me write these out. That's a 3. And these are balanced. That's good. I have NH4 plus and plus Br minus. So which of these guys are going to be our acid and base products here? So basically you look at kind of these ions, and you can figure out what could have been the acid base reaction for these products here. So what we want to do is we want to look at these guys here, and we want to start, we can start writing the kind of equilibrium reaction for these guys. So now the NH4 here is going to be a weak acid. It's going to, combined with water, it can dissociate into ammonia and our hydroxide ions. So let me write that down for us. And I'm only just going to write this one because this one is exactly the same. The ammonia for 1 and 5 here are exactly the same, so I'm only going to write this once. So here's NH4 plus H2O is in equilibrium with this is NH3 plus H2O. As you can see here, this is a weak acid. And you also have Cn minus here, which is going to be a weak base. It's going to accept a hydrogen here. So in this case, you can say this would be, well, actually, you can replace H2O with Cn minus if you really wanted to here. And you get NH3 plus HCN here. And this is going to be, again, you have your weak base here, and you have a strong acid. Or you can say weak base and strong, sorry, weak acid and strong base here. So this one is not a strong acid, strong base, so you can simply cross this out. LiNO3 here, this one would actually be a strong base and strong acid. And why we know that is because I have lithium. I can make lithium hydroxide from it, which is a very, very strong base. LiOH plus NO3. If I were to protonate NO3 here, this would be HNO3, which is nitric acid, and this would actually make our lithium nitrate, which is our product, plus H2O, and would not be in equilibrium. So this one would be a strong base, strong acid salt here. So this is our correct answer. And if you look at the other ones here, you could verify this one as well. NH4 Br is exactly kind of the same thing as this guy here, but you, instead of making the HCN, you make HBr. LiPO4, if you pronate this phosphate ion, you're going to have phosphoric acid, which is a weak acid here. Weak acid plus a strong base with lithium hydroxide. And then with Na2CO3, you would get a weak base. So let me write out, so for this one, let me write out the other guys. So NH4 is exactly the same. So this one is same as 1, but Br minus becomes HBr. So this is the same as number 1 here. Let me write that more clearly. And then this one's kind of the same thing as lithium hydroxide, except PO4 here is not as strong. Strong acid. It's actually a weak acid here. So I can write down LiOH plus, you could write H3PO4 if you really wanted to, or HPO4 2 minus. It doesn't really matter. They're all weak acids here, and you would get this would be in equilibrium, sorry, and you get LiPO4, Li3PO4, plus you would get H2O, and this would be in equilibrium. And because the only reason why we know that is because H3PO4 is a weak acid. So this is a weak acid strong base. So this is not correct. And then finally we have something like Na plus and CO3 minus. Na plus here would become the spectator ion. So in this case here, I'm focused on the CO3 minus. Plus if I add H2O to it, I would get, so this here is my carbonate anion. I would get HC or H2CO3. Or it become HCO3 minus first, plus OH minus here. So we know that this here is going to be our weak base here. So this is a good this is kind of a good good exercise here to figure out what this guy what this guy could be. And yeah, this is our answer here is lithium nitrate here. So this is our solution. So this is good. So lithium nitrate is a salt resulting out of a strong acid, so a nitric acid, and a strong base, which is lithium hydroxide. So that's strong acid, strong base salt. So the solution is correct. And as you can see, they also wrote down the chemical formula for that one as well. So the solution is correct. Okay, number 3. Ask us draw the carboxylic acid produced from the acid hydrolysis of butyl acetate, or butyl ethanoate is the IUPAC formal name here. So I want the carboxylic acid from acid hydrolysis of butyl. I'm going to use butyl ethanoate because it's IUPAC. Butyl ethanoate, and that might be something you're more familiar with if you're not familiar with the common names just yet. So I want the carboxylic from acid hydrolysis of butyl ethanoate. So let me draw butyl ethanoate first, and this would look something like this. So for butyl ethanoate, I have 4 parts. I have 2 parts. Sorry, I have the butyl part, or the alcohol part, and I have the ester part, which is ethanoate. So we know that this part is the alcohol, and this part is the ester. Let me, oh, sorry. This is the alcohol part, and this is the ester part. So let me draw the alcohol part in blue first, and I have butyl, so simply just a 4 carbon chain, so like that, like so. And then I'm going to draw my ester part in red here, and this is going to be bonded to my ester. Oh. My ester, which is going to start here. So it's going to double bond O. Let me draw this bigger, actually. This will be double bond O here. And then this here is my ester group, like so. And this here was my alcohol group of the butyl here. So this is my ester, and I have ethanoate here. So actually, the alcohol part is going to go the other way. So my apologies here. So let me move this So I'm going to start with, let me start with the ester part here instead. So I'm going to double bond O, and then this is the 1, 2 in carbon because it's FN, so it's 1 and 2, and this here is going to be my alcohol part, which is going to be bond to 4 carbon. So 1, 2, 3, and 4. So this here is my structure for butyl ethanoate. Again, you can see I have a butyl group, so 1, 2, 3, and 4, and then my ester is 1 and 2 for the ethanoate here. So this is the correct structure for butyl ethanoate. And what I want to do is I want the carboxylic acid from acid hydrolysis, right? So I can say that this is in. Let me rewrite the name here. So this is butyl ethanoate. And what it's going to do is going to undergo a hydrolysis reaction, an acid catalyzed hydrolysis reaction. So if I were to, and this is in equilibrium, if I were to add acid, or I have water here, and I have some type of acid here, so, or let me, yeah, I would have some type of acid. So I can say maybe, I'll just write acid because I don't know what acid is. It could be HCl, HCl4, doesn't really matter here. If I were to acid catalyze this hydrolysis reaction here, I'm going to cleave this bond here. So this water is going to come and it's going to cleave this ester bond here to make a carboxylic acid and an alcohol. So it's going to make my carboxylic acid, which is going to be this red part, and my alcohol, which is going to be my blue part. So let me draw out the red part for you, which is going to be ethanoic acid. So that's going to be my answer for this problem. So I have an OH group, bond to a double bond, O, bond to a carbon here. So this is here is my ethanoic acid. And then it's with that, the alcohol part is going to just be simply the butanol that's left here. So this here is the butanol. So this here is the acid catalyzed reaction. The acid hydrolysis of butyl ethanoate. So butyl ethanoate, and then I use a hydrolysis reaction with the acid as a catalyst. I'm going to make ethanoic acid. So so it's this part here. It makes the carboxylic acid. Let me highlight that in red here. So this part makes the carboxylic acid. Oh, sorry. And this part would make the alcohol here. And you can think of this as the OH here is kind of like secretly bonding here, and we're using water to cleave this, and that's why we get the water back as our catalyst here. Get our water back because this is OHO, and then I'm adding simply an H here and an H here as well. So this here is our answer. So ethanoic acid is our answer because we only care about the carboxylic that's produced. So this here is our answer, which is ethanoic acid. Let's see here. So it's acetic acid plus 1 butanol. So again, 1 butanol is here, and about ethanoic acid, which is basically acetic acid. And they use the common name in this case. It doesn't really matter if you did not use the common name. So ethanoic acid is correct. So the solution is good. It's good analysis as well. Okay. Number 4. Which of the following are correct for zero order reactions? So I actually don't have a question that's given here, so I might just have to look at the solution for me to solve this here. But I can just but what the solution says here, because I'm not giving a question here, it says which of the following, and I don't have anything. So I'm just going to let me just check the solution to see what they're doing here. So this is about for zero order reactions. So it says here, a zero order reaction has a constant rate that is independent of the concentration of the reactants. The rate law is simply rate equals K. So this is correct, right? So when we're saying the rate here, which is simply just R, equals, we know there's a rate constant times some type of concentration. We can say it's X or Y here. And X or Y here. And these are going to be the reactants. So X and Y are the reactants. And in a zero order reaction, our R is simply just equals to K because it is independent of of the concentrations here. The exponents here are simply 0. So if I add those up again, if you take anything to the power of 0, it's simply just 1, right? So you get k times 1 times 1, which is simply just equal to k here. So it's independent of the concentration. So it does not rely on these concentrations of my reactants for the rate to progress. So the rate simply just equals k. So this solution here is correct. So it says, unlike the other orders of reaction, 0 order reaction has a rate that's independent. That's good. So if I increase or decrease the concentrations of X or Y, it does not affect the reaction rate. So this solution here is correct. And that's simply what, and that's kind of what the definition of a 0 order reaction is. It's just independent of the concentrations of the reactants. And even if you increase or decrease the amount of concentration, you can't affect the reaction rate. It's simply just dependent on this K value here. So the solution is correct. It's a good analysis as well. And you could read on as well, but that's kind of the general gist of what a 0 order reaction is as well. All right. Number 5. How many valence electrons are in fluorine? So again, you can think of these two concepts as if you understand Bohr-Rutherford, you can solve this problem, and if you also understand electron configuration, you can also solve this problem. So it depends on what context this question is asking in terms of what course it is. I'm going to assume it's probably a lower level chemistry course just because of how it's phrased. How many valence electrons are in fluorine? They're not asking you about the electron configuration or the principal quantum number of fluorine. So in this case, I'm just going to draw a Bohr-Rutherford diagram. And what we can do is we can put F in the middle. There's actually 2 ways to solve this. This is the longer way, and I'll show you the easy way after. 1, 2, 3 here. I have 3 shells. And let's see, I'm going to have fluorine has 1 and 2 in the first shell, like so. So I have 1 and 2 here, and then it has 1, 2, 3, 4, 5, 6, 7 in the second shell. And I'll write this in red because these are my valence electrons. Because I know that my valence electrons, or valence E minus here, or this is my shorthand for electrons, valence electrons are the outermost electrons in the atom. When you say outermost, it's the outermost shell here. So this is 1, I have 2 here, 3, 4, 5, 6, and 7. And this here is the Bohr-Rutherford diagram of my valence electrons, and I simply all I have to do is count the electrons in the last shell, and you can see 1, 2, 3, 4, 5, 6, and 7. So therefore, you can say that fluorine that's really bad. Fluorine has 7 valence electrons. And this here will be a correct solution for this answer. If you want the shortcut to figure out valence electrons in fluorine, you can just simply look at the periodic table here. And a good kind of general rule is that the group number here determines the valence electrons. And this doesn't really work with the multivalence. It only works with kind of group 1, 2, and then 13 to 18 here. So for example, my valence electrons in group 1, they're all 1, right? I have 1 valence electrons in this group. I'm going to have 2 valence electrons in the second group. I'm going to skip the transition metals because they can be multivalent, and sometimes they carry different charges. So in this case, I'm going to skip the valence electrons. Group 13 will have 3 valence electrons. Group 14 will have 4. Group 15 has 5. 16 has 6. 17 has 7. And we can see that fluorine belongs to group 17. So therefore, it has 7 valence electrons. And finally, 18 would have 8 valence electrons here, or a full shell here. And these are noble gases. So in this case here, all you have to do is find fluorine on the periodic table, which is here, and look up to the group, and you see 17. And as you get 17, we know it's 7 valence electrons. So there's a bunch of ways to solve this problem here. And obviously, if the context of the question was in a grade 12 question, and if I were to ask the electron configuration, like what they did here, we can always write out the electron configuration. So let me do that for you as well. And that's what they're doing with this solution here. So fluorine, so I want the electron configuration of fluorine. So you can say F here can be fluorine, can be made up of, let's see. So I can go back to my periodic table here. I have electrons in this guy here and this guy here. So I have electrons in the 1s2, in the 1s orbital. We have 2 electrons in the 1s2, or in the 1s, sorry. I have two electrons here in the 2s orbital. So you can say 2s2. And then finally, because fluorine exists here, it belongs in my p orbital. In this case, the 2p orbital. And we have 1, 2, 3, 4, and 5. So I'm going to have 2p5. So we have 5 electrons in the p orbital. And as you can see here, my principal quantum number, or the n value here, is the biggest number that you see, that you can see kind of in your electron configuration. In this case, it's 2. And therefore, the valence electron you can calculate is simply just a sum of all the electrons in that principal quantum number. So this is going to equal, again, 2s2, it's going to be equal to 2 plus 2p5, which is 5. So 2 plus 5 here is equal to 7. And this is also our solution to figure out the valence electrons in fluorine. So as you can see, they did the electron configuration as well, and they got it correct. So 1s2, 2s2, 2p5. And as you can see, the highest principal quantum number is 2. So therefore, there are 7 valence electrons in our fluorine here. So the solution here is correct. And again, many, many ways to think about this problem, but it depends on the context of the question and what course it's asking us in. So the solution is correct. Good analysis. Okay, number 6. I want the systematic names of these compounds, so spelling counts, okay? And as you can see, the solution here is, like, I think there's a formatting error. I'm not sure what's happening on the, like, this is, I don't know, I can't decipher this at all. So there's something wrong with this. But I'm going to say solution is incorrect, I guess, because it's not complete. But we will look at filling this out. So this is number 6. So I want the names. So name each compound. So I have CuI in a solid state. I have Fe2O3 in a solid state. I have COF2 in a solid state, and I have FeO in a solid state here. So what I want to do with these compounds is if I want to name these guys here, the trick to this question is these metals here. So I have copper here, I have iron, I have cobalt, and I have Fe here, or iron here. And the trick here is that I have all these metals here are multivalent metals. So they exist in 2 different charges, or 2 or more different charges. So multivalent metals. So therefore they have more than one charge. So why do we care about multivalent metals? Well, it's going to affect the naming of these metals, right? Again, for example, copper has a 1+ charge or a 2+ charge as well, depending on which state it's in. So in this case here, what I want to do is I want to look at how this guy dissociates. I'm going to break up this solid into its ions. So I'm going to simply say this would be copper and iodine, right? Plus iodine here. And as you can see, iodine here is one of our, you could think, I'm not going to balance this chemical equation, but you can think of this as iodine. Again, we know it's a diatomic, so this here it's definitely I2, so therefore there has to be a 2 here. But we don't really want to think of this as our as a balancing kind of chemical equation. We want to think about the naming here. So in this case, I care about mostly the charge, right? So this here is an I- charge, because I know iodine exists in the fluorine in group 17, where fluorine, chlorine, bromine, and iodine exist in. So I know the valence electrons are going to be 7 valence electrons. So I have a charge of 1- here. And I have to figure out, how do I balance out this 1- charge on copper? Well, I need a 1+ charge, right? Because 1 plus -1 is going to give me 0, right? So therefore, copper, in this case, I will have a 1+ charge. So therefore, the naming, I can easily figure out the naming, right? Because once I figure out the charge of copper, this is an easy name, right? This is simply just copper. So I can name this and say it's copper. Let me use brackets here. So this is copper, and then I put the charge here, which is 1. So copper 1, and the iodide for the naming of iodine. We just drop the INE and we change it to IDE. So this is copper 1 iodide is our solution for the first problem here. Our second is going to be our iron here, right? An iron here is also a multivalent compound, right? So let's again break this up into, and all these are multivalent, by the way. So we have to break this up into, again, 2 compounds here. So if Fe, and I don't know the charge of Fe first, plus I know the charge of oxygen though, right? Which is O. I know it's 2 minus, and then I think again I'm not gonna balance these chemical equations, so I have 2 minus here. So in this case, I have a 2 minus charge here, and I want I want something that's that would give me kind of 2 irons here and also 3 oxygens here, right? So you could think of this as there's 2 ways to think about it. Again, you can think of this as a crisscross method, where basically the charge of the number here of iron here, which is Fe2, belongs to this charge here. So therefore, the oxygen with 3 would have to be belonging to this charge here. You can think of it as that kind of problem, or you could think of it as, oh, there's two irons here and there's 3 oxygens here. So therefore, I have in total 3 times 2 minus here is a 6 minus charge, and this guy also has to be a 6. So I need to balance out the charge of 6 minus, so I'm going to need a 6 plus, obviously, and 6 plus divided by 2 here is going to be equal to 3. So in this case here, this would be a 3 plus charge. So again, there's a lot of ways to think about this problem here, but it's again up to you of how to think about this problem. But the crisscross method, I find, is kind of the quick and dirty way to kind of finish this problem, where you can kind of just figure, oh, I know that this oxygen has 3 here, so therefore this has to be a 3 plus. So you can think of it that way, but it's up to you in terms of how to think of that, how to think about this problem or how to approach this. So again, I have simply Fe is simply just iron, and then I put the charge here, specify the charge, which is 3 in Roman numerals, and oxide is going to be the name of this compound here. Iron 3 oxide. Number 2, I'm going to go a bit faster now. I have cobalt and fluorine here, so I'm going to write CO, and I don't know the charge of CO here, plus fluoride. Now the fluoride has a charge of 1 minus, right? Because again, it belongs to my halogens. If it has a charge of 1 minus here, and I have 2 fluorines here, what am I going to do? Well, I have a charge of now 2 minus, right? I have 2 fluorines here, which means I have a charge of 2 minus. 2 times -1 here is -2, or 2 minus. So which means cobalt, in order to balance out the charge, is going to have a charge of 2 plus, right? Because 2 plus 2 minus -2 will give me 0. So therefore, you can say that this compound is going to be cobalt, so COBALT, cobalt 2, and then fluoride. And that's going to be the charge, that's going to be the name of that compound as well. And finally, let me make some room here. I have this compound here is going to dissociate to Fe something plus O and then 2 minus. And as you can see, we only have 1 of each, guys. We have 1 iron and 1 fluorine, or sorry, one iron and 1 oxygen. So this is a charge of 2 minus, which means I need a charge of, what charge do I need to make this 0? Well, I would need a 2 plus charge, right? So therefore, this is a 2 plus. And I can say that this compound will be iron, and the charge of iron, which is 2, and the oxide. So these are very, very tricky, right? When we talk about iron 3 oxide and iron 2 oxide, they're very different compounds. As you can see, Fe2O3 and FeO are different compounds here. So again, the solution is incomplete. So solution is incomplete. And then I'm going to say that CuI S I'm going to say the naming or the name, or yeah, CuI. So for CuI, copper iodide, copper 1 iodide, the charge on copper is 1 plus, Therefore, the name of the compound is copper 1 iodide. And then I'm going to copy and paste these guys because I'm going to have to write this up 4 times here. And then I'm going to just simply modify these guys here. So let me space this out. Formatting. This is Fe2O3. The charge on iron here is going to be 3 plus. Therefore, the name of the compound is going to be iron. This is iron 3 oxide. And then this is for copper, or sorry, for cobalt fluoride here, or cobalt 2 fluoride. The charge on cobalt is 2 plus. Therefore, the name of the compound is cobalt 2 fluoride. And then finally, for this compound here, it's FeO for FeO here. The charge on iron here is going to be 2 plus. Therefore, the name of the compound is going to be iron 2 oxide. And this is the full solution for this problem here. So the solution is incorrect because I can't decipher this problem here. Let's do number 7. The conjugate acid of CH3NH2 is what the conjugate acid. CH3NH2. So all I'm going to have to do is write out the equilibrium of the reaction, right? So I have CH3. I'm going to start with this guy here, CH3 and H2. I'm going to add water to it. I'm going to dissociate into. So as you can see, this here, CH3 and H2 here, I'm going to actually, this here is going to accept an electron, right? So this here is going to be CH3 and H3 plus, right? NH3 plus. It's going to accept a hydrogen from this water and then get OH minus here. And again, these are all in aqueous solutions. You could put AQ here. Water is in liquid. There's AQ. There's AQ as well, if you want to be really specific with the states. And what we have here is, what do we have here? Well, we have, this is methylamine here. I have water. And this is going to give away, or sorry, this is going to accept a hydrogen from this water here. So in this case here, if I'm accepting a hydrogen, this here is going to be my base, right? So this here is a base. In this case, a weak base, because I have a Kb of some value here. So this here is a base. As water is behaving as an acid, I'm donating a hydrogen here. So here's an acid. So therefore, my conjugate acid is simply going to be the conjugate of methylamine here. So this is going to be my Ca, or my conjugate acid, which makes this one my conjugate base here. So my conjugate acid, or Ca, is going to be this guy here, CH3 NH3 plus. And as you can see, this answer is correct. CH3 NH3 plus, and it says conjugate refers to the relationship between acid and base, right? So this here is the base, and this here is the acid, the conjugate acid and base pair. So CH3 NH2 and CH3 NH3 plus as well. So the solution is correct. Good analysis. Let's do number 8 here. It says balance the following equation in acidic conditions. Okay, so I want to balance in acidic conditions. So I'm going to have, this is C2O4 2 minus, I think. O4 2 minus plus MnO2 is going to yield Mn2. Is this Mn2? Oh, Mn2 plus. Ah, yes, Mn2 plus. That makes more sense. because manganese is not diatomic, Mn2 plus, and CO2. Okay, so what I want to do, if I want to balance in acidic conditions, this is going to be kind of a redox kind of reaction here. And we know that this here is a redox reaction because it's telling you to balance in acidic conditions. So what we want to do is we want to figure out the half kind of equations for us to figure out if we're balancing. We want to figure out the half equations and we want to add them together. So that's kind of our goal here. And in this case, we know that it's in acidic conditions here. So we want to separate the half reactions first. So that's our kind of first step here. So let's do that. So our half reactions mean that I care about the CrO4 2- and our CO2, and then our manganese dioxide here and our manganese here. So let me write this down. So I'm going to have C2O4 2- is going to go to CO2. And then I have MnO2 is going to go to Mn2 plus. So in this case here, what I'm going to do now is I'm going to then balance elements other than oxygen and hydrogen. So in this case here, in the first one here, I have 2 carbons and I only have 1 carbon on this side. So I'm going to add a 2, right? And then in this case here, it actually balances out the oxygen as well, because this is 4 oxygens here and 4 oxygens here, which is good. And manganese in this case here, manganese here is I have 1 Mn and 1 Mn here. So that's okay. That's good. But what I want to do now is I will need to start adding some electrons, right? Because again, the charges here are off, right? So I have C2O4, and I have 2C and 4 O's here. But this guy has a 2-. So therefore, I need to add a 2- charge as well here. So I'm simply going to add 2 electrons, right? And this will now balance out my charges as well. So my elements are balanced, and also my charges are balanced as well. For this half reaction, so as you can see, this one is good, right? So they did that here on this step here. And similarly with Mn or manganese dioxide, I have Mn here, Mn here. And then what I have to do here is, again, I balanced out my manganese first, but then I have to balance out my hydrogen and oxygens, right? And in order for me to do that, I can always add water. And water is a great kind of method here because it introduces oxygens into my compound here. So I have 2 oxygens here, which means I'm going to have to add 2 waters to this side. I have 2 H2O on this side. And then therefore, if I have 2 H2Os on this side, again, I have here, this is 2 oxygens and 2 oxygens on this side, but I want to also introduce 2 times 2 is 4 hydrogens on this side. So therefore, I'm going to have to balance out 4 hydrogen on this side as well. So I'm going to add 4 H plus. And we have abundance of H pluses because we are in an acidic condition here. So this is 4 H plus MnO2 here. Now what we can do here is we have to balance out the charges, right? So you can see here, I have 4 H pluses and then I have 2 pluses here. So I have to make these both equal to each other. And again, I can't add protons, but I can add electrons. So instead of bringing this number 2 plus to a 4 plus charge, I'm going to bring down this 4 plus to a 2 plus charge. So if I want to do that, I simply have to add 2 electrons, right? So 4 H plus MnO2 plus 2 electrons is going to yield Mn2 plus H2O. So this here, as you can see, this here is going to be my balanced half reactions for this compounds here. So this is good. So what we can do now is we can, so that's what they did here, right? MnO2 plus 4H plus 2 minus is equal to that. That's good. And now what we can do is we can actually examine our 2 equations and to see if things start balancing out. So this is equation 1. And this here is equation, let me maximize this. This here would be equation 2. And we can see what balances out from both sides, right? In this case here, we have the same number of electrons, right? So this cancels out, electrons here and electrons here cancel out. And I believe that is it for that electron, because I don't have any CO2s on this side or C2O4s on this side. I don't have manganese dioxide on this side and manganese on this side or water. So I simply just have to put these together to get my answer, right? So I have C2O4 2 minus plus I have everything on this side here, which is 4H plus MnO2 is going to yield everything on this side. So 2CO2 plus Mn2 plus H2O, or plus 2H2O. Sorry, I forgot the 2 here. Plus 2H 2O. And this here is the solution for my problem. And they got, believe they got the question right. They have C2O4 2 minus plus MnO2 plus 4H plus, which is good, yields 2CO2 plus Mn2 plus 2H2O. So this solution is correct. Good analysis. And all we're doing here is we are balancing. First, what we want to do first, we want to separate them into our half reactions. We balance all the elements besides hydrogen, oxygen. And then with those, and when we want to balance hydrogen and oxygen, we simply can add water, because water is very, very readily available in all electrochemical reactions. And then what we have to do is balance out the charges. Depending on the addition of the hydrogen proton, we can add some electrons to both sides. And then all we have to do is put the half reactions together and see which things cancel out. So usually the electrons cancel out, and maybe some other compounds also cancel out as well. And then we can rewrite this equation as one equation as well. So solution is correct. It's a good analysis here. Was number 8. Number 9 is asking kind of the exact same problem. So let me, this is also asking a balance equation in acidic conditions. So let me write this down. Balance in acidic conditions. So again, we have H3ASO3 plus I2 would give me H3ASO4 plus I minus. So again, what we want to do is we want to separate them into our half kind of reactions here. So I have H3ASO3 is going to yield H3ASO4. And then I have I2, which is going to yield I minus here. So let's balance out these guys here. So I'm looking at this here as equation. Let's look at the first equation first. So here's equation 1. Equation 2. So let's look at equation 1 first. So I have H3. So so again, well, I want to balance everything besides the hydrogen and the oxygens first. So I have arsenic here, which AS. I have one arsenic on the side, which is great. And then now what I want to do is balance out the hydrogen and the oxygen, right? So hydrogens are already balanced here. So I have 3 hydrogens here and I have 3 hydrogens here. However, my oxygens are not balanced, right? I have 3 oxygens here and 4 oxygens on this side. So what I'm going to have to do is I'm going to have to add a water to this side for us to get 4 oxygens. So I have H3ASO3 plus 1 H2O. This would give me 4 oxygen in total. 3 plus 1 is 4. I'm going to yield H3ASO4. However, if we introduce our hydrogens here, I'm going to have to balance it out, right? So as you can see here, I have H3 and H2 here, which means 3 plus 2 here is 5 hydrogens here. And I only have 3 hydrogens on this side. So what I'm going to have to do is I'm going to have to add 2 H pluses on this side for us to balance out the hydrogens here. So as you can see, I have 5 hydrogens on both sides now, which is great. But now we have another issue, which is the charges, right? The charges here are off, right? I have a 2 plus charge here and a 0 charge here. So I want to make this a 0 charge. So if I want to do that, I simply have to add 2 electrons to the side to balance out the charges, right? So I can add 2 electrons to the side. And this will be a balanced half reaction for this arsenic part first. And then what I can do now for number 2 is I can balance out the second half reaction here. So if I2, let me do this in black. I have I2 to I minus. So first what I'm going to do is going to balance out all the elements that are not hydrogen oxygen. In this case, we only have iodine. We have 2 iodines on the side and 1 iodine on the side. So we just simply have to add 2 to the side to balance out the iodines first. And as you can see here, I have now a 2 minus charge on this side here and a 0 charge here. So I'm going to have to add electrons to my left side for us to balance out those charges. And what I can do is I can add 2 electrons to the left side, right? So let me modify this. And I can say I can add 2 electrons to this side here. So now both of these guys, my charges are balanced, right? I have a 2 minus charge on this side and also a 2 minus charge on this side. So this is good. So what we can do now is we can look at both our reactions here. We can look at the products. We can look at what can we cross out here. And as you can see here, we can cross out the electrons, right? So the 2 electrons can go away from this side and the 2 electrons can go out from this side. And I believe that is it for those for that kind of half reaction. So what we could rewrite here is we could rewrite our balanced chemical equation. So we have H3 ASO3 plus H2O, and then plus our I2 here is going to yield H3 ASO4 plus I have 2 hydrogens here, and then plus 2 I minus Cs here, plus 2 I minus Cs here. And this is going to be my balanced chemical equation in acidic conditions. So as you can see here, let me see if this solution is correct. So I have H3ASO3 plus H2O plus I2 yields, I believe the question mark is yields, H3ASO4 plus 2H plus 2I minuses. So the solution here is correct. Solution is correct. Good analysis. I'm going to say analysis says somewhat there. It wasn't as detailed as the other one. Solution is, I'll just say solution is correct. I believe that the question mark is a yield sign instead. So you would have gotten something like that or something like that. That would make more sense here. So I have H3ASO3 plus H2O plus I2 would yield H3ASO4 plus 2 I minuses plus 2 H positives. So this solution here is correct. And finally, my last problem here is number 10. And I'll end off this problem, this session, with this question here. So it says, which statements are consistent with Rutherford's nuclear theory as it was on only, I think it's cut off here. Nope. Let me see if I can, maybe I'll download this file and see if I can actually read the question here. Second. Yeah, so it says, which statements are consistent with Rutherford's nuclear theory as originally stated? Why? And we have 4 of these guys here. So it says the volume of an atom is mostly empty space. The nucleus of an atom is small compared to the size of the atom. Neutral lithium atoms contain more neutrons than protons, and neutral lithium atoms contain more protons than electrons. So let's look at C and D first, because this is looking at lithium atoms. So let me draw out a lithium atom here. So I know a lithium atom. I have a lithium atom here. And how many protons does lithium have? Well, I can look at my periodic table and see that lithium belongs in number 3, right? So my atomic number is 3, so therefore I have 3 protons here, which means this has 3 protons. And in a neutral atom, I want to balance out the charges, right? So I have 3 pluses, which means I'm going to have 3 electrons in a neutral atom. And how many neutrons would I have? Well, in this case here, 6.94 is a lithium, is my atomic mass for lithium. I can kind of round this to kind of 6.94 is about 7. So I can say that my atomic mass is 7. So I can say the number of neutrons, I know that neutrons is going to equal my atomic mass minus number of protons. In this case, my atomic mass, I'm going to round to 7. I'm going to minus 3 here for number of protons. So my number of neutrons is going to equal 4. So in this case here, for C and D, neutral atoms contain more neutrons than protons. So this one is, this C is correct, but is it consistent? We don't know. Number D here says neutral lithiums contain more protons than electrons. This one would have to be false. So we know that off the bat, D here is false. Now let's look at number A and B. Now A and B says the volume of an atom is mostly empty space, and this statement is true, right? Because the volume of an atom is mostly empty space. We have the nucleus, which is the biggest part of the atom, and then we have orbitals or electrons that are surrounding the atom as well. And it says B here, it says the nucleus of an atom is small compared to the size of the atom. This here is false, right? Because then the nucleus atom actually makes up most of the size of the atom here. So if B, we know that B and D are false, so we're just looking at A and D here. And both these statements are true, but which one is actually consistent with Rutherford's nuclear theory as it was originally stated? So what we want to do is we want to figure out, okay, what the heck is Rutherford's nuclear theory, right? So we want to say it. We want to say this kind of is the gold foil experiment. If you're not familiar with that, and let me just look at let me just summarize what the nuclear foil experiment did. And basically what he did was he put kind of a it might be better if I actually gave you a diagram instead of me explaining it. So let me just Google this, and Rutherford's gold foil experiment, and let me see what we can do here. I just want a diagram, basically. No, that's not a very good diagram. This one? Nope. Let me see this one here. So I kind of like this one. This one's actually pretty clear. So it says here, I have like some type of screen here, and I have an alpha particle emitter. And what it's going to basically shoot out alpha particles onto this gold foil. And we have screens that are surrounding this gold foil. So basically what we're doing is, or what Rutherford was trying to explain here, was that do most of the alpha particles go through the gold foil, which is what he proposed before. But he also saw that the detection screen, he also saw that there were alpha particles that would reflect off the screen onto multiple angles here. So this here is the arrow or the rays that you see bouncing off this gold foil. So as you can see, B here is most of the alpha particles go through, but some of them actually reflect onto different angles here. So knowing that, it means that his conclusion here basically states that most of the electrons go through, which means the volume of the atom is mostly empty space, right? Because most of the alpha particles are going to go through, and alpha particle compared to atoms are much bigger than those ones as well. But the ones that are being reflected, it means that they're actually hitting the nucleus of the atom here. And as you can see, this here is the nucleus of the atom, or the electron in this case here. And some of them are going to reflect onto different angles, right? So those are my conclusions of here. And as you can see, the summary here is good, right? It says bombardment of gold foil with alpha particles showed that some particles were deflected. So it means the nuclear model of the atom consists mostly of small, dense, positively charged interiors surrounded by a cloud of electrons. So therefore, what we can say about the statement here is that A is true, right? The volume of an atom is mostly empty space because most of the alpha particles are going through the gold foil here. So A will be our correct solution in this case. And let's see. I don't know. Oh, it says answer. The statement of volume is mostly empty space is consistent with Rutherford's theory. So this solution here is correct. And let me see if they have an explanation here in the text here. So it says, according to Rutherford's nuclear theory, most of the space in the atom is empty and tiny negatively charged electrons are dispersed throughout the volume of the atom. Therefore, the statement is true. So solution is correct. Good analysis. So you can say that Rutherford's gold foil experiment concluded that that the size of the atom or the volume of the atom, the volume of an atom is mostly empty space because most of the alpha particles, and they're big compared to the atom, went through the gold foil. So this solution is correct, and it was good analysis as well. So that makes my 10 problems for the day. Again, thank you so much for watching. Again, all of these videos are going to be posted on our YouTube channel at youtube.com/OneClass, and you can access those videos as well. My name is Joey. I stream math from Monday, Wednesdays, and Fridays, and I stream chemistry on Tuesdays and Thursdays, so you can check me out then. Again, thank you so much for watching. Stay safe, stay healthy, and have a great day. Take care.